Okay, we're going to continue on here. Chapter 3, still bonding, I think. Why not? So last time we got into, obviously, chemical bonding a little bit more, really more covalent type of bonding. And we talked about, again, the three sort of types of bonds. Again, we have ionic bond, which is between a metal and a non-metal. And once again, based on those sort of properties or periodic trends, that's always going to result in, again, a transfer of electrons, resulting in a cation formed, which is positively charged, and again, an anion formed on the non-metal side that's negatively charged. And again, it is that opposite attraction there that holds that together. Again, no sharing of electrons. We have sort of on the other end of the extreme, non-polar bond, which is a covalent bond. And that is between two nonmetals. And as we talked about, because they are both nonmetals in this case, they have very similar sort of periodic trends. And again, neither one's going to want to give up its electrons. So we are at a sharing situation. The deal with the nonpolar covalent bond is we have equal sharing of electrons. And in the middle is a polar covalent bond, or just a polar bond. And once again, that is also between two nonmetals, which means they will also share electrons. But again, here the sharing is unequal. Remember that we can use the change in electronegativity values to help us determine whether or not a bond would be a polar bond or a nonpolar bond. We could also use it for ionic, like we talked about, but in most cases, you really don't need it. As we mentioned, as soon as you see metal, non-metal is going to be ionic, so you don't really actually need those differences. But if you do calculate the difference in electronegativity values and get anywhere from 0 to 0.4, that is considered a nonpolar bond. And that would be obviously a covalent bond, sharing of electrons. Above that sort of 0.4 knockoff there, or cutoff, to below 2 will get you some type of polar bond. And as we talked about, not in every situation, but typically if you get some type of different above 2, you're going to be looking at really those electrons transferring, and you're going to get an ionic bond. Once again, just some metal, non-metal is pretty much all you need for that, so you don't really need it. We also talked about the idea that you really, in a lot of cases, do not necessarily need the actual values. You could kind of use the general trend in electronegativity to help you make a pretty educated guess, especially if you're comparing two things that are in the same period on the periodic table. Whoever is further to the right should be obviously more electronegative, and that usually will give you some type of polar bond. Also, if you're comparing anything in the same group up and down on the periodic table, once again, whoever is higher up in the group should also be more electronegative, and again, would most likely give you a sort of polar bond as well. The only ones you have to watch out for is kind of this couple of things we talked about, where there is that, as we saw in the non-metal region, obviously that diagonal sort of relationship between a couple of elements like copper, I say copper, carbon, which is like copper if you pick the U off of it. So that is carbon and sulfur. They're diagonal of each other, so one is further up, but the other one's further to the right, so they sort of cancel out their differences. And it usually isn't directly diagonal from each other. It's kind of like down and over one is usually where we get that. Thank you very much. Now, with that being said, we talked about how to draw Lewis structures, which is really important. And again, you do want to follow these steps in drawing our Lewis structures. Remember, one of the first things that you really want to figure out is kind of how it is connected, how everybody is really connected. I would say, again, in our situation in this class, a lot of times we do have just one central atom, but sometimes you could have multiple central atoms within a molecule. But typically speaking, the least electronegative atom should be in the middle. We should never find fluorine or hydrogen in the middle. I'll just write no. Don't do that. Yes. So we never put those guys in the middle again, because hydrogen will have too many bonds, obviously too many electrons, and fluorine is the most electronegative element you could have. So clearly it should never be in the middle. Once you do that, you probably the most important thing is to count up the total number of valence electrons. Remember, again, valence electrons equals the group number on the periodic table. And we do want to add them all up, including if it happens to have a charge. So we do have to adjust our count for anything that does have a charge. If it's negatively charged, got to add some. If it has a positive charge, you need to subtract some from your total. That number is really important, as we talked about, because you got to hit it right on the nose, exactly that number, no more, no less. It has to be exactly that number when you draw your structure. Once you do that, you just want to simply make now a single covalent bond from the center atom to all of the outside atoms. Once you've done that, you want to fill up the outside atoms as pairs of electrons until you pretty much have filled up all the outside atoms. And if you happen to still have electrons at that point, then you could go to the center atom and put them on as pairs of electrons. Again, everybody should have 8 except for hydrogen that should only have 2. At that point, if you have distributed pretty much all of your electrons that you counted up there in number 2, you want to make sure, again, everybody has met the octet rule. Our hydrogen has 2. It's at that point, again, we want to kind of start with single bonds. And it's at that point, if we do need to fix something, we do want to try to fix it by making a double bond and sort of exhaust, again, all of our double bond sort of options. And if that should not fix it, then we should move on to a triple bond. So as I mentioned last time, again, you don't want to kind of double bond, triple bond right out of the box. You do want to kind of think about it as sort of saving it to fix the situation. And also really important is, again, not drawing these things in sort of like piecework, if you will, each individual sort of element, and figuring out this guy has this many electrons, this one has this many electrons. What you want to think about is sort of just distributing the electrons over everybody, sort of working outside and then in. So you want to work on the outside in. Now, if you do have 2 central atoms, which is possible, you still would do the same thing. You work on the outside and then you kind of work in to do that. Any questions on that? All right, so we were in the middle, go back that way, I think, of drawing some of these. So we did up through CO2, I think. So we got SO2, CO3, 2 minus, and N2, huh? SO2, SO2, CO3. Got SO2, CO3, 2 minus, and N2. I don't think I did I? I did SO2? Huh. Not CO2? No, we didn't do SO2. I think what's up there is what I did, I think. Yeah. So these are the ones I did. Yeah, okay. So I think we did the first 3. So I think we did NH4 plus, CO2 or S, and SH2 we did. Otherwise it disappears somewhere. Well, let's do SO2 again here, just to make sure. Hopefully it'll be the same. Well, there we go. So we're gonna do SO2. So again, we want to go valence electrons. So sulfur is group 6. We have 2 times 6 for the oxygen. It's 18 valence electrons. Once again here, if we look at the periodic table, we got oxygen and sulfur in the same group. Once again, going up in the group is more electronegative, which means really sulfur should be in the middle. Oxygen should be on the sides, or up and down, however you want to put them, I suppose. Again, we're going to do 1 single bond to each of the outside ones. So that's going to be 2 and 4 electrons. That's going to leave us 14 more to go. Those will go on the outside. So 2, 4, 6, 8, 10, 12. At this point, I am done with the outside, but I still have 2 more electrons. that is going to go on the central atom as a pair of electrons. And by the way, that's how those dots get there, not double bonded everywhere on this one, just so you know. So that is what we're looking at. Now, when we do look at this, we can see everybody's good except here our sulfur, right? Our sulfur actually 2, 4, and 6 electrons, so it is short. All the oxygens are okay. We got 2, 4, 6, 8, and the guy on the other side is exactly the same, so he has 8 as well. So this is a situation where we can make a double bond to try to fix it. And in this case, we could double bond either to the left or to the right. So remember, though, that when we do take a double bond, I'll darker circle it, I guess. We're going to take these pair of electrons and bring them in. That will give us something that looks like this. This is also one where we could have double bonded again to the left there, and that would give us a resonance structure that we talked about, where the double bond would be here on the left. Single bond would be over here on the right. Again, if we count up all the electrons that are on this, we still only have 18, 2, 4, 6, 8, 10, 12, 14, 16, 18. Everybody has 8 electrons, and this would be the correct structures there for SO2. Any questions on that one there? It would be incorrect. So you do need to distribute those electrons. So again, if you follow sort of the instructions of how to do it by distributing them, that's how you get there. That's a super common error that people make, and that's because they just want to kind of double bond up out in the box, and you miss out on those sort of electrons. So the way you want to think about it is this: I really shouldn't be laying up any type of double bond or triple bond until I've already distributed all my electrons that I started with. Yeah. So as soon as you do that, then you can do the double bond and triple bond, and that will keep you out of trouble in most cases when you're trying to draw something. Yeah. Other questions on that? Okay. So let's take a look at CO2, CO3, 2 minus. Has some of those numbers, I suppose, in it. All right, so CO3 2 minus, that's going to be 4 plus 3 times 6 for the oxygen. Here we do have a -2 for carbonate. We're going to need to add 2, right? Minus means it gained electrons. 2 is how many it gained. So we'll have a 2 there. That's 18, 20, 24 valence electrons in this particular case. Again, if we look at the periodic table, carbon and I can put my carbon here. Carbon is further there to the left than oxygen, which means oxygen is more electronegative. As I mentioned before, we got 1 carbon and 3 oxygens, so that's going to put the carbon really in the middle. We're going to do 3 oxygens on the sides here. 1, 2, 3, that is 6 valence electrons. That's a lot. 18 left to go there. We can go on the outside ones as pairs. So 2, 4, 6, 8, 10, 12, 14, 16. Use some thoughts there. And 18. Once again, here we are now out of electrons. And everybody is good here except for our carbon. Again, it's a little bit short. It has only 6 electrons. Once again here, double bond should fix that. And in this case, all the oxygens are identical to each other. So you can do any one you want. So we'll take this and drop it in there to make our double bond. That will give us a double bonded oxygen up on top. Single bonds on the sides here for carbonate. We also will put a little bracket around it and a -2 on the outside. This again is another one that we can draw a resonance structure for. Draw a little higher here. Again, we could do, if we wanted to, let's draw a little higher here. We could double bond to the left. Would be easier to see, I think. And we could also have double bonded over here. I'll just steal this structure right there and use it. And obviously we need to get rid of a pair of electrons there. And we could double bonded there to the right. Any questions on any of those there? Once again, those electrons are delocalized, which means they are moving around. So at any given time, they could be at any of the oxygens that are present. And that's why we could draw more than one Lewis structure, because one doesn't really adequately describe sort of what is going on. Any questions on that one there? All right, then N2 here. So that is 2 times 5 for the nitrogens, which is 10 valence electrons. In this particular case, there really is no central atom, but you can still follow pretty much all the same steps that we did before, and it will get you to the right structure. So in this case, we're just going to put them side by side since there really is no central atom. And we're going to do the same thing. We're just going to connect them with a single bond there, and that single bond represents 2 electrons. That means we have 8 electrons to go. They're both nitrogens, so it doesn't matter which one you start with. So I'm going to put some dots here. So 2, 4, 6, and now 8. At this point, we have now used up all of our electrons. Nitrogen on the right's all good, right? But the nitrogen on the left, not so good. It has only 4. So again, we're going to try to fix this by making a double bond. So we're going to take a pair of electrons in to do that. That's going to give us a double bond there. And we'll look like that. Did that fix the situation? It did not. We got closer. We're now at 6, right? So instead of 8. At this point, there's no option for any more double bonds. So now I want to triple bond. And this is how the triple bond gets there. Again, we're going to take a pair of electrons in to do so. And now we will have our triple bond. And now both nitrogens there on the left and the right will now have 8 electrons around it. And we still have only a grand total of 10 electrons in this particular case. Again, this is sort of the order as which you want to go. Single bond up, everybody. If there's a problem, double bond. If there's more problems, try to another double bond if possible. If not, move on to a triple bond. Like I said, at the point of a triple bond, it should work unless something's really, really wrong. Any questions on drawing those things? Yeah. Now let's try a couple more here that maybe let's scribble on this page. I guess we'll use it. Why don't you draw HNO3, which is nitric acid? And I'll give you a hint. The connection is, well, hydrogen is attached to one of the oxygens. So kind of looks like this. Why don't you also draw C2H2 and see what you get there? So why don't you draw the Lewis structures for both of those? Okay, let's take a look. So once again here, we got a couple different ones here, but we still want to approach it the same way. So again, if it's obviously something that I think you would not know the arrangement, I would give you sort of the skeletal arrangement like I did here on the first one. We still want to figure out our valence electrons. So we got 1 for the hydrogen, we got 5 for the nitrogen, 3 times 6 for the oxygens, 18, 19, 24. Now, in this particular case, there's actually 2 central atoms, but everything works the same. So we're still just going to start with just a single bond to everybody, regardless. And that is 2, 4, 6, 8. We appreciate there. That is 16, I think. We're still going to work our way from the outside in. So am I putting dots on hydrogen? No is the right answer there. So we don't need anything. We're going to go other outside then. 2, 4, 6, 8, 10, 12 at this point. I still got 4 electrons to go. At this point, really, the next outside one is the oxygen. Again, kind of working outside to in. So we can put some dots there and some dots there. That is 4. That is 0. At this point, we have now placed all 24 of our electrons. Is everybody good in this case? No, the nitrogen here is short, right? It's only got 6. So just like what we normally do, we would need to make perhaps a double bond to fix it. We actually have three options to make a double bond. Probably the one you maybe shouldn't choose is, which one doesn't look like the other two? This one, yeah. By the way, this is what makes it an acid. That's the hydrogen that comes off that makes it an acid. So probably don't want to play too much with that one. So you could double bond either of the other two. For example, we could take these in there, and that would get you a structure where we got a double bonded up on top and single bonded that way. Also could do a little resonance action on this guy by double bonding to the guy to the left and keeping that guy up on top single bonded. Perfectly fine as well. And that is nitric acid right there. Yeah. We will see it in like experiment 7, I think, in nitric acid. Any questions on that one? So again, even if you have more than one central atom, it doesn't necessarily matter. You still just want to kind of follow your steps that we talked about and it will work. This over here is a organic molecule. And you pretty much know it's an organic molecule where you see a bunch of carbons and hydrogens and other things thrown in there, like sometimes oxygen and some other things. The way that pretty much organic things are put together is carbons are attached to carbons, and then pretty much the hydrogens are attached to the carbons, and that's pretty much the way that it works. We know that hydrogen's got to be on the outside, right? Because it cannot be on the inside, otherwise we'll have too many bonds. So in this particular case, we know that logically speaking, we got to have perhaps some type of arrangement like this. Now, you may be wondering, could you put both hydrogens on one carbon? The answer is yes, but in this case, it probably won't work out so well for you. So my advice is if you have multiple hydrogens and multiple carbons, try to like spread them out equally-ish around the carbons. And that's usually will get you sort of the right idea. We still want to figure out basically how many electrons. So that's 2 times 4 for carbon, 2 times 1 for hydrogen. I hit another 10. 10. There it is. Still going to do the exact same procedure that we've done before, which is a single bond. So 1 single bond, 2 single bonds, 3. That is 2, 4, 6. Leaves me 4 electrons. Still going to do the same things we've done before, which is work outside in. Outside are hydrogens, which we know we're not going to put any dots on those. So that means we're going to work our way in. If you want, you could fill up 1 or spread them out. It really won't matter in the end. So I'm just going to put them all on 1 carbon, which will give me 2, 4, 6, 8, 10. Is everybody good in this case? This carbon is a little short, right? So this carbon has only 4 in this case. So again, just follow our normal procedure. When we're short, we're going to double bond it. Going to bring a double bond in there. And now that carbon on the right got better. It got to 6, but it is still short. So at this point, we need to make a triple bond, yeah, and bring it in. And that will get us here a triple bond known as ethine here, which is this organic compound right there. Now we still have maintained 2, 4, 6, 8, 10 electrons. Both carbons now by triple bonding it up again have reached the octet. We did not try to do any triple bonding or double bonding with hydrogen again because that would give it too many, right? And it has no electrons to do that with. Any question on these sort of multiple atom type things, central atoms? No. Question on drawing loose structures in general. Professionals, I like it. All right. All right. Now let's talk about what's on this page that I wrote all over. Let me get rid of what's on this page list. Let's see. Let's get rid of that there. All right. So the next thing we're going to talk about is something that perhaps you most likely have not discussed before in terms of bonding. And this is what is referred to as formal charge. I shouldn't say that. Maybe you have. I don't know. But formal charge in Lewis structures. And what the formal charge is basically the difference between the valence electrons in the sort of atom by itself and the number of electrons that it's assigned in its Lewis structure. The number of non-bonding electrons, the number of bonding electrons that it has. It essentially will give you, in a sense, the sort of charge that atom would have if sort of, the electrons were kind of fully transferred. but they're not in most cases because, again, they're sharing these electrons. So it's sort of the charge in the arrangement of that Lewis structure, what they take. To calculate the formal charge, you pretty much take the number of valence electrons in the atom or element, atom of the element. You minus it from the number of non-bonding electrons. These are individual electrons, so like 2, 4, 6, 8, the number of electrons. Those are the dots on your Lewis structure, right? So those are all the guys with the dots. Minus 1/2 the number of bonding electrons. Those are pretty much your lines on Lewis structures. You could do this for every single element that you have in a Lewis structure. All right, so let's take a look at one and sort of see how we calculate it. So for example, here, if we take ozone, looks something like this. There's basically 3 oxygens. We could calculate the formal charge on each of these oxygens. So we'll start with the double bonded oxygen. So the formal charge on that guy is 6 for oxygen, which is its normal number of valence electrons. When we look at the double bonded oxygen, it has 2, 4 non-bonding electrons. Again, not pairs here, but actual individual sort of electrons. So 4 total non-bonding or lone pair electrons. Minus 1/2 the number of bonding electrons. Each line represents how many electrons? 2, right? So that's 2, and that line is 4, right? 4. So that is 6 minus 4, which is 2, minus 1/2 of 4, which is 2. That means that this oxygen is carrying a 0 for its formal charge. Now, if we go to the single bonded oxygen, which looks like this, the formal charge would be, once again, 6 because it's oxygen. That's how many valence electrons that oxygen has. Minus the number of non-bonding electrons, so that is 2, 4, 6, minus 1/2 the number of bonding electrons, which is 2. That is 6 minus 6 is 0, minus 1/2 of 2, that is a -1. So this guy right here, that oxygen in that arrangement is carrying a -1 formal charge. Lastly, we have the oxygen in the middle, which is double bonded on one side, single bonded on the other, basically. And if we look at the formal charge for this guy, once again, it's going to be 6 minus 2, as those are the non-bonding electrons, minus 1/2 here, obviously, of 2, 4, and 6, since we have 3 lines. That is 6 minus 2, which is 4, minus 1/2 of 6, which is 3. That is a +1, yeah. Overall, ozone is neutral. Yeah, it has no overall charge, right? And when we add up the formal charges, it actually still equals 0, right? But in reality, the oxygen here that's single bonded is carrying a more negative sort of situation, while the oxygen actually in the middle is carrying a more positive situation. And the guy on the left there that's double bonded actually has no charge type situation. Question on how to calculate that. So we could also, again, look at carbonate here. And why don't you calculate the formal charge on all the elements in carbonate? So for each of those 4, what is the formal charge? Bless you, for each. Okay, so let's take a look. We'll start, why not? We'll start with the double bonded oxygen. Once again, we're going to calculate the formal charge. We're going to start with the number of valence electrons in oxygen, which is 6, minus, again, in this case, there are 2, 4, minus 1/2 of 2 and 4 for our bonding, going to give us 0. By the way, you might notice that's the same one we got last time we did that one, because it's the exact same bond. It will always come out the same, right? So if we take our single bonded oxygen, again, our formal charge here will be 6 minus 2, 4, 6 non-bonding electrons, minus 1/2, again, 2 that is there. And that's going to give us 6 minus 6, which is 0, minus 1/2, 2, -1. So this guy has a -1, and this one has a -1. Obviously, again, they will come out the same if you did the guy on the right or left. It's basically the exact same bond. That leaves us our carbon in the middle, which is bonded all around like so. So for carbon, that is 4 minus 0, as there's no non-bonding electron, no dots, minus 1/2 of, there are 4 lines, which basically means there's 8 electrons. And that will give us a formal charge of 0. Yeah. In this particular case, the -2 for this polyatomic ion is actually hanging out there on those 2 single bonded oxygens, is where that -2 comes from. It does match the overall charge, by the way, which typically the formal charge should sort of match that. It should add up to the overall charge of whatever it is. If it's neutral, it should add up to 0. And if it's not, then it should add up to the charge. Question on that there. So who cares, right, about formal charge? Why should we care about formal charge? Well, there really is sort of a more practical application of formal charge and drawing Lewis structures, which is, you ever wonder to yourself, why can't I like hook this thing up differently and draw this thing differently? Or why should I not triple bond out of the box and end up with a triple bond rather than, say, a single bond? We use formal charge a lot of times if you are maybe undecided as to, well, I think I could draw this structure 2 different ways or 3 different ways. Maybe I want to put somebody else in the middle versus this one. We could use formal charge really to help us decide between structures which one is really a better structure and which one is not such the greatest structure based on formal charge. So a lot of times we use formal charge to help us decide between structures of, which one's a better structure than something else. So there are some rules that we want to follow when we're trying to decide between structures, which one is perhaps a better move. So for neutral molecules, a Lewis structure where there's no formal charge is preferred. So essentially speaking, if you draw 2 Lewis structures and they're good in terms of, distributing electrons, everybody's got 8, everybody, that needs 2 has 2. The better structure is usually the one where you could get everybody down to as many zeros as possible in terms of their formal charge. What that does is reduces sort of the overall charge on all the individual atoms, and that's sort of your best situation. Like, if you could hit all zeros, that's like golden. That's probably really your best structure that you should draw. Or at least if you can minimize to a lot of things getting down to zeros, that's really good. Typically speaking, if you draw Lewis structures and you start calculating formal charges and you end up with relatively large formal charges like +2s, +3s, +4s, really big ones, those are probably less plausibly the good structure to keep. Now, when you're choosing among a couple of different sort of structures, you definitely would want to choose the Lewis structure where the formal charge that is sort of more negative, for example, ends up on the more electronegative atom. So if you have a choice between 2 and you kind of have even distribution of like the numbers, but you end up with like a negative formal charge, a larger one on like something that's less electronegative, and the more positive formal charge on something that's more electronegative, that's probably not great. That's because if somebody's more electronegative, they're most likely going to do what with the electrons? Bring them towards itself, right? And that should probably make it a little bit more negative in that bond. And that's why when you have that option, the one that is more electronegative ends up with a negative formal charge is probably, again, a better than the one that's more electronegative and a more positive formal charge. Any questions on that? So for example, if we were to draw formaldehyde, right? These are 2 possible sort of drawings that we may end up. Again, instead of putting the hydrogens all together, maybe we want to split them up into two other elements. So calculate the formal charge on each of these and decide which one should be the better formula or structure based on formal charge. Okay, so let's take a look, see how you're doing. We'll start with the guy on the left. We'll start with the hydrogen. So the formal charge on the hydrogen is 1 because that's what it has for valence electrons. There's no dots or lone pairs, so that's -0, -1/2 of 2 for our bonding electrons. And that's going to give us a formal charge of 0 on that guy and 0 on that guy, so not too bad to start with. We'll take a look at our carbon here. And here carbon is 4. It's normal valence electrons. Does have 2 non-bonding electrons. -1/2 our bonding. There's 2 there, 4 there, 6 there. So that's 4 minus 2, which is 2, minus 1/2 of 6, which is 3. That is a -1, if I am not mistaken, right about there for our carbon. We take a look at the oxygen here, also double bonded, kind of a similar bond happening there. Formal charge on it will be 6 minus 2, that is there, -1/2 of also 6 in this case, again 2, 4, and 6. So that's 6 minus 2 is 4, minus 1/2, which is 3. That's a +1. So in this case here, we have zeros on the hydrogens, we have -1 on the carbon, and we got +1 there on the oxygen. Coming over here, we know hydrogen will actually come out the same. So we got zeros happening there for our hydrogens. We'll do our double bonded oxygen, which is 6 minus 2, 4. -1/2 of 4. Again, 2 and 4 for our bonding. That's giving us 6 minus 4, which is 2, minus 1/2 of 4, which is 2. That is 0. And now our carbon in the middle, double bonded and single bonded, that would be our 4 minus 0, as there's no lone pairs, 1/2 of 8 in this case. 2, 4, 6, 8. And that's going to give me a 0, yeah? So based on formal charge, which one's better? It is this one, right? This one obviously didn't minimize the formal charge to zeros, which don't necessarily has to minimize them all to 0. They're not extremely large, the formal charges here, either on the one on the left. But one of the other problematic things with the one on the left is between carbon and between oxygen, which one is more electronegative? Oxygen. But in this case, oxygen is carrying the more positive formal charge, right? And the least electronegative guy in that group there is actually carrying the more negative one. That's also not a great situation. So even though it's not necessarily a large formal charge, the distribution of those formal charges are not so great in terms of their charges, where we have now the more electronegative one having more of a positive one formal charge, which would not make great sense since this can be bringing the electrons towards itself. Question on that there. All right, try a couple more here to decide. Let's just do why we can't triple bond maybe, or maybe we can triple bond CO2. So use formal charge to help you decide between those two. And I don't know, we'll do these. Why don't you do this one down here? You just get the ones in the middle. All right, so calculate the formal charge, decide which one of these guys here and those two groupings are the better structure. Okay, let's take a look. So we'll start with up on top here. We'll do our triple bonded CO2. In case you're wondering if you could triple bond there instead of doing 2 double bonds. So if we do our single bonded oxygen there on the left, looks like this. We have for the formal charge 6 minus 2, 4, 6. minus 1/2 of 2. That's going to give us a -1 here for the formal charge on that guy. Our carbon in the middle has a triple bond on one side and a single bond on the other. That's going to give us for the formal charge 4 minus 0 minus 1/2 of 8, which is 0. Carbon's all good. And if we look at the triple bonded oxygen, very rarely seen. Let's see. Formal charge here, 6 minus 2 minus 1/2 of 6 for our 3 bonds there for the triple bond. Gives us 6 minus 2 is 4, minus 3 is +1. So that is the formal charge sort of distribution here. Any question on those calculations? Looking at the double bonded CO2, again, we have our double bonded CO2, our oxygen there, and our formal charge would be 6 minus 4, like we've done before, minus 1/2 of 4, and that's going to give me a 0 on each of those. And now if we do, again, our double bonded carbon, that's going to give us 4 minus 0 minus 1/2 of 8, which is 0. The better structure is the double bonded up. Yeah. So again, this is why we oftentimes will double bond our options until they're done before moving on to a triple bond. And the reason why we just don't lay up a triple bond on it, right? Is it possible to have that structure? Maybe, but it's not the best structure. And when you're drawing loose structures, you really do want to try to draw the best structures. And this, again, formal charge is one of the big things that can help you decide between structures. Now, when we look at N2O here, right, we have options. And in this option, we decided to throw nitrogen in the middle. And on the other option, we decided to throw the oxygen in the middle, right? And our normal sort of rules would be that the least electronegative should be in the middle. So let's see if that works out good in the situation or not. So let's take a look at the nitrogen here on the left. That's going to be for nitrogen. We're going to have 5 minus 4 minus 1/2. And again, we have double bonded there. So that is 4. That is, dare I say, a lot of math there. That's still thinking about the math. That is -1. Go with it. It's going to get the calculator out in a second. All right. So we're going to go nitrogen in the middle, which is double bonded actually on each side. That would give us a formal charge of 5 minus 0 minus 1/2 of 8. So that's basically 5 minus 4, which is +1. So we have a +1 in this situation. And we've done our double bonded oxygen a number of places, including up here. So I'm just going to steal the calculation from up here, as it will come out the same. And we will have a 0 for that one. Again, basically 6 minus 4 minus 1/2 of 4 in this case for that particular guy. All right, so that is our distribution there on our first structure. Second structure here, we have basically the same nitrogen on the end, so it's going to come out the same as -1, as it's the same as the guy on the left. We have, in this case, a double bonded oxygen on both sides. Very creative here. So actually, let me go up with this one. I'll go here. So for this guy, we have 6 minus 0 minus 1/2 of 8. So that's basically 6 minus 4, which is a +2. So this guy will end up with a +2 formal charge. And obviously here, our nitrogen on the right-hand side is the same as the left-hand side. So we should also end up with a -1, which is basically this calculation right here on the bottom right there that we did previously. All right, so which one's better? It is the first one, right? So this is better. It has minimized the formal charge at least down to 1s. Remember that if you start hitting 2s and 3s, that's not so great. Also problematic with the big +2 on this one is what? Between nitrogen and oxygen, which one's more electronegative? Yeah, and now it's carrying a big positive formal charge, not so great, right? So again, here we minimize definitely the formal charge on the oxygen to 0, which is better than +2 for sure. And again, we have a smaller distribution of formal charges on the guy on the left. So it did follow our normal rule of the least electronegative in the center, right? So here we got our nitrogen in the center. Again, why those rules are there for these reasons. Any questions on A, how to calculate formal charge, how to use it to decide between things? Do you have to use it to help you decide? No, you could, unless it asks you to draw the best structure based on formal charge. So that's usually how those questions are. Like here, they'll give you a couple of structures and ask you to choose which one's better based on formal charge, or they'll say draw the best Lewis structure based on formal charge. If it just says draw a Lewis structure, you could lay up any one. You should still follow the rules that we talked about, least electronegative in the center and all those type of rules. Any questions on any of that there? All right, so let's talk a little bit about resonance, which we did, but let's talk more about bond length. And I like that my check marks were previously there, so that's good. Makes it easier to check mark, I suppose. I'm going to circle them now. So you do not have to obviously memorize this list of bond length. The bond length is obviously the distance between the two nucleuses, right, and the bond between the two atoms. But if we look just at our carbon-carbon single bond, it's 154. If we look at the carbon-carbon double bond, it's 133, and it is 120 for a triple bond. If we look at the carbon-nitrogen single bond, it's 143, double bond carbon-nitrogen 138, and triple bond carbon-nitrogen 116. The trend we see is every time we slap on a bond, does the distance get further or smaller between things? They do get closer. That's because to make a double bond or a triple bond, you're going to be bringing in electrons to do that, right? So now you're bringing in even more negative between the two. That's going to cause the nucleuses, which are positive, to come in, right? So every time you slap on a bond, you're going to get a lot more negative distribution in between the two atoms, and that's going to drag them closer to one another as well. That also relates to strength, as I believe they say. In terms of bond strength, a triple bond is actually stronger than a double bond, and a double bond is stronger than a single bond. It's not like a double bond's twice as strong or anything like that, or a triple bond's 3 times as strong. But that's the general sort of trend. And that goes with our bond length. That single bond is longer than a double, than a triple. I think of it this way, like if you had a brand new shiny pencil out of the box, it's nice and long, you could snap that thing no problem, right? You take a couple chemistry tests or just one, and you're down to an eraser and a nub like that big. Very hard to try to break that, right? So, the distance between gets much closer, everything gets closer and stronger, and it's harder to break it. All right. So we talked about electronegativity scale there. Talked about that. Now, as I talked about, and we did sort of talk about when we were talking about electronegativity and bond polarity, again, we can use those differences to help us determine it. And remember that as we talked about in terms of bond polarity, there is just that one place where bond polarity and molecular polarity, as we talked about, is basically the same thing. And this is when you're dealing with diatomic molecules. So again, if you have a diatomic molecule, because it has only one bond, if that bond is polar, that means you will have a polar molecule. And if that one bond is nonpolar based on electronegativity difference, then the molecule will be nonpolar. So as we talked about, obviously F2, that's going to be an electronegativity difference of 0. And that means that that's a nonpolar bond. And once again, this guy would also be a nonpolar molecule, because that is the one and only bond, as we talked about, that's in there. Same thing if you had something like what we talked about, HF. Again, if you do the electronegativity difference, That is a 1.9 difference, which means, again, we have a polar bond, which we could represent with that bond dipole arrow pointing towards the fluorine in this case, which is more electronegative. And that would also mean that this would be a polar molecule because, again, that is the only bond that's present. And as I think we talked about, which was, I think, a question last time, that would also be the dipole moment. So only polar molecules will have a dipole moment, which means overall distribution of electrons within the molecule as a whole is unequal. And in the case of diatomic molecules, again, that is the only place where both bond polarity, where we use difference in electronegativity, and molecular polarity are the same. We're going to talk more about molecular polarity in chapter 4, about things that are 3 or more atoms. Again, there's a little bit more to it than just that. And that's what we see here. 0 in terms of our dipole moment, which means nonpolar molecule. Each of these have a dipole moment, which means these are polar molecules. You can see the giant dipole moment here. That's because electrons have jumped ship, right? That's an ionic compound, so there's definitely a big separation of charge in an ionic compound as well. All right, so we did that. So speaking of energy and bond strength, let's talk a little bit about bond energy. And this will be probably one of the only times we do any type of energy sort of calculations, if you will. And when we make bonds and when we break bonds, these are both an endothermic and exothermic type process that's occurring. When you have a bond that's together, it's an endothermic process, which means energy needs to be put in. When you put in energy to that bond, everybody gains energy. They're able to break away from each other. When you want to make a bond, everybody's moving around really fast. You have a lot of energy. They have to release some of that energy, slows them down, and allows them to come together and basically make the bond. So making bonds is a exothermic process, and breaking bonds is an endothermic process. And we could calculate the delta H of the reaction, which is the change in enthalpy. Which is basically the overall sort of heat gained or lost in the reaction based on bond energy, or is sometimes referred to as bond enthalpy as well. And remember that delta H, as we probably touched upon, will tell you what type of reaction you're dealing with. If you end up with a delta H value that is positive, then you are dealing with an endothermic process, which means heat and energy is absorbed. If you end up with a delta H that is negative, which looks like a positive if you write a positive sign there, I suppose, but let's get rid of that. Negative. It's a exothermic process, which means, again, our heat and energy is released rather than absorbed. So how do we calculate the delta H of a reaction based on bond energy? It's pretty straightforward. The easiest way to do it is pretty much you add up all the bonds you break, which is essentially what she has to do to make the reaction go. And then you add them to all the bonds that you make. Yeah. And really the difference in the energy is the overall delta H. So if we take a look at this here, and we'll take a look at one to finish up on how to do a calculation like this. So let's just say that we had this table here, which obviously would be provided for you. And let's just say we have this reaction here, just very badly drawn there. So we'll do, we'll just do this here. Actually, let's do this one. Let's do H2 plus O2 make some water. Yeah. A little bit of 2 there, 2 there, perhaps. Yeah. All right. So If you wanted to calculate the delta H using the bond energy here, or bond enthalpy, the first thing that you really want to know is what bonds you're breaking and which one you're making. So on the reactant side, all these bonds here has to be broken. And on the product side, we have to make all these bonds that are over there. Also really important, which is how this ties into Lewis structures, is you probably should know the actual structure of it. So you know which bonds you're making, what type of bonds. As we just saw, right? If it's a single bond versus a double bond versus a triple bond, different energy values. So you have to kind of know what you're dealing with. So we know that hopefully H2 is H and H single bonded, right? But there's not just one of them, there are two of them, which means we actually have two of those bonds that we need to break. Oxygen is, if you're not sure, actually double bonded. Yeah, so it looks like that. So we need to look up the value for a double bond. We hopefully know what water looks like, something like this, right? But again, there's not just one of them, there are two of them, which means we have two of these, right? So really at this point, it's all about just keeping track of everything. So we'll start over here on the left. And what we're going to basically do is add up everything that we need to break. So clearly here we have two hydrogen-hydrogen bonds that we need to break. Each bond requires 436 kilojoules of energy to break. So that's going to be 2 times 436 kilojoules, right? We are also going to break one oxygen-oxygen double bond, right? So we're going to add that to our one oxygen-oxygen double bond that we're going to break, which is right about there, 498 kilojoules, right? So 498 kilojoules. I'm going to add all these together, which is basically 2 times 436 plus 498 tells me that the amount of energy that I need to bring to the table here to break all those bonds is about 1,370 kilojoules of energy. Breaking bonds is endothermic, right? Which means the sign here should be positive, right? It's an endothermic type process. Any questions on that? Now let's talk about everything that we're making on the other side. So in terms of making bonds, in each of the waters, there's how many OH bonds? 1 and 2, which means I have 1 and 2 in that one. I am making essentially 4 oxygen-hydrogen bonds. That's basically what I'm making on this deal. I'm going to look up oxygen, hydrogen. I didn't scribble on it, so that's pretty good. It's right about there. 464 for each. So I'm going to take that and times it by 464. That will give me 4 times 464, 1,856 kilojoules of energy. When I make bonds, is it endothermic or exothermic? It's exothermic. And exothermic values should be negative, yeah? So technically this should be a negative value. Now I have all the energy required to break the bonds. I got all the energy required to make the bonds. All I have to do now to figure out the delta H is add those together. So the delta H would equal, for this reaction, my positive 1,370 kilojoules to break, plus my negative 1,856 kilojoules to make. So we add those together and we get, or subtract them, however you want to look at it, I suppose. You end up with a negative 486 kilojoules for the delta H of this reaction. Overall, this reaction is endothermic or exothermic? It's exothermic. There's a net release of energy in this case when you make water. Yeah, so it gives off energy actually when you make some water molecules in that process based on bond energy. Yeah. question on how to do that there. So definitely when you're doing this, drawing a quick Lewis structure, if you're not sure what the structure looks like or what type of bonds there are, is a good idea. It also is a good idea because it just visually lets you kind of see all the bonds. It's very common. People oftentimes will miss bonds, especially if there's something with like two center atoms. A lot of times people always kind of miss the guy in the center. They think about all the outside ones. They don't think about any of those bonds sort of in the middle. All right, we're laid up there for today.